and populating half of the room. I'm going to conclude this series of lectures I gave, which focus on the bright side of the cosmos, with particularly going into galaxy formation and evolution. The outline of this talk will be first to show what we know about the modeling, our idea. When I say our, it doesn't necessarily mean it is mine. In fact, I will show some points in which there is disagreement and controversy nowadays, which are very interesting. But there is a scheme in your cosmological model where galaxy should form and evolve in a certain way. Then I will explain again how we assess the physics of galaxies, which doesn't come straight out of data or out of simulation. And I will then present a series of key results for you to remember, some of which are currently unexplained. And I will finish, if I have time, with the pure cosmological application of stellar population modeling, which is the cosmic chronometers to assess the expansion of the universe. So people like White and Rees and others, at the end of the 70s, they put forward, so the problem was, let me tell you this, because this I really studied at school, there were scenario to form galaxies, the most interesting of which was called monolithic collapse, developed by Larson at Yale and Egg and Linden-Bell, in which there is a large gas cloud, a collapse out of its own gravity, and by collapse it starts to cook stars, build up metallicity, and in this way you get a fantastically looking galaxy which is massive as a metallicity gradient and form very fast. I will argue at the end of this talk this is what we need for massive galaxies actually. But the drawback of this scenario was it was not included in any cosmological model. So you can do an isolated simulations, but when you decide what is your cosmic web, it is a harder time to make individual monolithic collapse for galaxies. In fact, the problem is we think we live in a lambda cold dark matter universe. And if this is the case, the halos of dark matter cannot but collapse hierarchically. There is an enhanced power on the highest density matter fluctuation, but still the whole process must be hierarchical and must be bottom-up. We know that if we swap, and I come back to this to the end, to warm dark matter, we can reverse the hierarchy. For the most massive galaxy, warm dark matter is better. The problem is it formed galaxy too late. And people observe galaxy at redshift 6, while warm dark matter needs more time. So remember that. The reason why this model became very successful is because if there is lambda, if there is cold dark matter, it must go this way. And because it explains well the large scale structure. That it gives you a lot of, we'll show the power spectrum. And other people, this is pretty well recommended, but for the baryons, it might be a different thing. In any case, in this scheme, as much as dark matter halo collapse hierarchically, baryons follow the hierarchy of dark matter halos and start to coalesce and form stars and merge as well as a function of cosmic time. Now, the immediate things that was evident to people long ago was, well, if I take the mass function, in this case expressed in pseudoluminosity of dark matter halos, it has a power law. The first question is, do baryons follow the same pattern of mass distribution as the dark matter? And it turned out not at all. Indeed, low mass galaxies are far less abundant than what the low mass dark matter halo would predict. High mass galaxies as well, to a different extent. The recognition of that call for the inclusion of baryonic physics, which you would say, well, it's trivial, galaxies are baryonic, I need to take into account baryonic physics. Correct, but it was not that trivial that the mass function should be different. In particular, as we will see, people advocate the effect of a supernova feedback to expel gas from low-mass galaxy. It works because they have a small potential well, which stop them forming and shine and making them into large number. At the high mass end, the supernova feedback regulates star formation, but they are insufficient to eject the gas outside of the potential well, simply because galaxies are much more massive. So what people have included in recent years, also thanks to work we have done, so I'm going to come back to that, is the hope that AGN, bright AGN in the center of galaxies, warm the medium outside and hamper further star formation. In this way, to avoid to have too bright galaxies which are not observed. So the first thing to remember is that the mass function of galaxies normalized in the middle shows a different and distinct behavior with respect to the host dark matter. The Ni is about 3 in 10 to the 10 solar masses. If you change the AMF, this is going to change a factor of 2. So it's roughly an indicative value. Now, let me go through main processes a bit quickly, and then we do this. Super, if you want to have a cartoon of galaxy formation. So, first galaxies, and I should have said, and I said this 2 days ago, parallel to the first stars, population 3, start to grow from matter density fluctuation, which you have because we have dark matter, because otherwise they are insufficient. That's also one of the problems. At a redshift that is unconstrained and be between 6 and 20. That's the same epoch of reionization. People debate on the actual agents of reionization. In a lambda CDM model, you have plenty of dwarf galaxies because you have plenty of dwarf halos. So if they could reionize after you put the stars in that, that would be good. Although observation, the super observation, so with really state-of-art but a bit pushy telescope, do not clearly support that things. The other option would be massive galaxies and quasars. And the Sloan made a breakthrough to observe the highest redshift quasars, which they find around 7, redshift 7, which is a good thing. But currently, this is something we are all putting effort in, either from the modeling or for the observation. What were the first structure? How did they reionize the universe? Their stellar ingredients, such as initial mass function, matter a lot. If your population was only made by massive stars, you get a lot of UV photons that break through the neutral gas. If you had instead the low mass stars put in your galaxy, then you need a hugely massive galaxy to do the same, which of course in a lambda CDM is quite complicated. After this happened, we know it's happened, you start to feed back in a positive and negative way. Joe Silk has written a nice paper a few years ago to highlight the feedback that's not only working stopping star formation, but also in triggering star formation. So this is a principal ingredient in simulation. Whenever your star exceeds 50 solar masses, the amount of UV photon is enormous, and you start to regulate what happened. Further in time, because first you need to make your supermassive black hole, you start to have your quasar in the center, or preferentially massive galaxies, who also will start accreting and emitting, or let's say triggering re-emission, and help as a regulator. It acts in 2 modes, as we will see. But if you talk to people studying AGN, doing really active galactic nuclei, they will tell you this will never work. And the reason is the AGN is as massive as you want, but this tiny little thing in the middle of 10 to the 12 solar mass galaxy, it doesn't help in regulating star formation on the whole scale. So here we have another for the simulation point of view, is a trick factor. I put an AGN and I put an if statement, such as if luminosity of AGN larger than that, star formation rate equals 0. This is the way people do, okay? Because the physics is very complicated. Again, it's interesting because there is discussion. Another thing that happens in the simulation, the first things you form are what we call bulges, which would be okay, because for example in the Milky Way the bulge is very old. But they keep forming along the redshift range because the universe is hierarchical. Accreted matter into these bulges start to settle around disks, which doesn't tell you that the galaxy is a spiral galaxy in a simulation. It contains an accreting disk. A further merger will actually break the disk. So as much as my talk will focus on problem at the massive end, the elliptical galaxy, notoriously, it is very hard to make a spiral galaxy like the Milky Way in simulation. Why? Because the disk is not stable, because every merger will break it. First. Second, the disk rotates too fast with respect to the actual rotation, so it doesn't live on the Tully-Fisher relation. So it's interesting, but there are problems. So this merger creates a disk, then people have figured out that there is another class of merger, which we call minor merger, where the mass ratio between the big galaxy and the accreting stuff is very little. Of course, minor mergers will not destroy anything. What do they do then, you will say? Well, they act in enlarging the size of the galaxy, mostly the radius rather than the mass. One problem may be that they can create gradients because they make up galaxy halos that are not observed. And I'm going to come back on that as well. Then a few years ago, when it was clear, it started to become clear the massive elliptical cannot sustain merger with much star formation, Peter van Dokkum suggested the notion of dry mergers, which are the mergers of identical large galaxies without invoked star formation. Why don't you want star formation? Because you make your galaxy too young, too full of young stars, and they don't look like that. A dry merger is a merger of two galaxies which don't have gas. So you need to have them old already, which is a little bit of a trick. And those is difficult to assess. I mean, there have been observations with Hubble Space Telescope of dry merging couples around redshift 0.8, but it's a bit shaky. So this is, in a nutshell, a recipe that includes your 99 concept, but not yet, but I will go to that. This is another thing useful for you, which is how galaxy formation models are constructed in far more detail. It is from a review by Carlton Bow, which I always find very useful because it tells you the cascades of events, and this is going to be common whether you have semi-analytic models or hydrodynamical simulations. The main features are the same. So you start with your cosmological model that gives you your initial condition. This hasn't changed much, although I should make you noticing that the change between WMAP and Planck allow galaxy to be a little older, so it has made some differences. And this has been studied and published by Simon White and his group. So you have then your structure of dark matter merging halos, which is very common in most simulations. So these are very, in a way, robust within our knowledge of these parameters. From here on, start the fun, in a way, and also the uncertainties. So here you start to build up the baryonic physics, with all its complications. The most tricky problem are cooling of gas. Gas will cool at some point into these potential halos. How much will cool? It is a function of the metallicity of the gas. For decades, this has been kept constant because it's a very difficult problem to treat. Then Joop Shaye and his collaborator have included element in non-solar ratio, and so iron with a lot of electrons, it acts as a coolant better than others. So here you have this problem of interplay. In the meantime, you have mergers which you cannot stop. I mean, there are tricks to stop like the AGN, but mergers come along with the cosmological web. You have to include feedback. Feedback from stars will depend on which initial mass function you adopt for your stellar population, which is not predicted by the growth of the model itself. You may have subsequent bursts due to the mergers. And then there the parameter is the mass of the burst, and also at which point of redshift it occurs. It will have a different metallicity and a different age spread. Very tricky to treat and presently not treated, and this is where actually we're all excited to put work, is the chemical evolution. Subsectively, the people take models like mine and make the synthetic population and let them evolve. But every time you have a population that dies out, the interstellar medium will be enriched, and in principle, your next generation should incorporate those byproducts. This is called chemical evolution. At the meantime, dying stars will pull back elements into the medium. So all this problem you have over there, finally, galaxies have dust. No? And they have dust just for the simple reason that the stars die and they leave products that end up, some of which is gas, other is dust. How do we treat them? It should be treated self-consistently in the model with a radiative transfer treatment, which is done in some simulation. It's very complicated, as I think Martin has shown yesterday. And of course, playing with dust, you exploit degeneracy of stellar population. You can make your galaxy fainter or redder at your leisure. But maybe this is not the real physics of the galaxy. Don't take me wrong, I'm not criticizing these things. I think simulations are probably at the present time even more important than data, because we have copious data and we have less explanation. So I like that, but I just want to highlight how it goes. So, unlike those of you who work on cosmology before the Dark Ages, the lucky thing with galaxies is that we see things. So we can attempt a dual approach in which we use data to constrain the simulation, which is semi-empirical or phenomenological, we will see. And also we can simulate the various aspects of galaxies because we are going to have observation that can probe them. So in general, the best approach is to use simulation to extract a physical parameter from data that can be traced back in the simulation. And then, this is very important, is to compare in both observed frame. This triggered a philosophical discussion in a few papers with Jim Gang and Conroy and our papers. And the example of this is the stellar mass of galaxies. In the simulation, it's a pure quantity. In the data, you need to model it on top, and there are uncertainties. So there I will show a result of the work. We prefer to put the simulation in the observed frame without going into this translation, finding interesting stuff. So the first part that we need to deal with is such that you, well-educated student, get all the complexity of this, is how do we get, so what are the key parameters that constrain galaxy formation? There will be some that do not constrain it at all. The people find it, morphologies, for example. People like to use Galaxy Zoo and look at galaxy. Morphology is not clean, okay? In the simulation, it's very hard to be defined. In the simulation, it varies all the time. And observationally, you can do it, but not to very high redshift. So it is, to go through the zoo of galaxies all over the universe is not a critic, but I don't think it's constraining very much. Instead, you want the physics. So, when did galaxies start to form? And when is the formation of the stars in galaxies, which may not be the same thing? How long was the epoch of star formation? Because this depends on your chemistry and the element abundance ratio effect. Supposedly you have created nice population with that. Do your galaxy also form and assemble with a mass that matches what it is observed? And the detail, the evil will be in the matches. But this is a statistical view at the galaxy population. So you need functions such as the mass function or the luminosity function to tell you, yes, I could make galaxies as they are, and I also could make them in the right number density, which are two different problems. And we will see that. Of course, the crucial ingredient is stellar population model, which you know from my lecture of the other day. So this is just an example on how the model fit is performed. Just as an example, you can do it different ways. These are just to use the BOSS data because we have been spoken about it very much. The data at these points, and the blue and the red are models. assuming different quantity of stars. So for example, here the red model is a galaxy with 10 to the 11 solar masses. And an age of 3 billion years, which should be seen at the redshift 4.1. And you have two possibilities. You fit a model without star formation, is the red. You fit a model that includes star formation, maybe because you like multi-parametric modeling, you want to constrain something more, and then you compare some statistic like the chi-square, and you compare the numbers that you get. So by fitting theoretical SED to data, you get your M-star, galaxy star formation epoch, if possible metallicity, and all the alike. Now, something that is discussed in the field of galaxy evolution, but you will understand this immediately, is that the properties you derive depends on the model you have used to derive them. So don't call them observational. They are not. They are not. It's like that. It's half of half. And in this paper, we show exactly what happens. And then you can keep using the model you prefer, but that is part of your initial prior. So this is a galaxy at redshift 2.5 from the Hubble Deep Field of the Hubble Space Telescope, meaning for this data set that the Daddy and collaborator have, you have 14 photometric bands. It's almost a spectrum. It's fantastic. I mean, you have much more possibility to fit the model properly. And then this is a part of a comparison between these two types of models, but you can do it in another way. You blindly take your fitter and put a model with different physics in it. So the red is now 0.4 billion years, which is pretty good at that redshift, because it would imply the galaxy started to form by redshift 3, which is okay. High metallicity, no dust. And you get actually a wonderful fit, okay? It also makes sense that the galaxy does not have dust because it's passive. The model is passive. And dust usually go together with star formation. Then you fit another set of model for the same parameter. Besides requiring more redshift, you would argue your chi-square estimator is not good, so you need to change it, okay? So you change it. Now, the bluer model is allowed to become as old as the data would like, okay? You have noticed that here, this blue model would not fit the near-infrared of the galaxy. So you need, how do you, now you know it, you need to put all the red giants for the model to fit. Then you do it like this, and this fit to the blue curve is better than it was before. It's still not as good as the red, but it is better. But your galaxy is now 2.6 billion years. Which at this redshift is older than the universe, which is a problem. It is a problem if you use cosmology to set your initial condition. In other approach, Zhang and collaborator in China, they leave the ages of galaxy to fit back cosmology. So they would fit and see what is the actual age of the universe. We usually, at least using this model, we don't match into this embarrassment very much. So this is to say, okay, you don't want this solution. The solution is unphysical. You throw it away. So you put a cut to the age of the universe. This is what most people do, even if they don't tell you. So if the age of the universe is 13.6, at different redshift, there will be a limit that your spectral fit should not exceed. In this case, these are the two best solutions from both models. They are very different in physics. The red model is passive, mildly young and metal-rich, no dust. The blue model is older, is metal-rich but with a different dependence on star formation rate, and is very dusty. In particular, for this galaxy, we could exclude the dust because the far-infrared detector looked at it and didn't find anything. That's important because it's a way of breaking degeneracies for this. But what I want to stress is that the red model gives you a mass that is 0.2, this roughly 10 to the 10 solar masses. The blue model gives you 10 to the 11. Now, please go to your simulation and see how many 10 to the 11 you have at redshift 2.5. That's the way you constrain it. Okay? But the important thing is, it's like using the Heisenberg principle. I always take this. You have your data. You need a model to, first of all, speak about your data. So you put your model, you decide that this will give you a path for galaxy evolution. So this is the first thing, the model dependence, and we can live with that. The second thing is something that I call in this paper the iceberg effect. And this is very important, and this, it has to do with the problem of deriving mass from light. When we are seeing the lecture of stellar evolution, a 100 solar mass star has a luminosity which is order of magnitude larger than any of the low mass stars. So if you have a galaxy which has experienced star formation, the light from the youngest stars will completely cover all the light of the small mass sun-like stars that are below. However, the former traces the light. The second one traces the mass. So this is called the light average problem or overshine, which you see in this model. The black is the total theoretical spectrum of a population that is 1 billion years old and has formed stars constantly. The blue is the contribution for stars formed in the last 0.5 billion years, which you see that is completely dominating the ultraviolet, which is this part, and the optical, and they start to become evident only in the near infrared. And the red is from the stars born in the first 500 million years. This is a log scale, which you don't see at all. So when we derive masses from data, the problem is, are we deriving the mass of the whole lot, which is what the simulation have, or are we deriving this? Because this is what is luminous. Of course, people are aware of this problem, okay? The problem is, how do we treat it? Of course, we need corrective function. And in this paper, we have actually shown in a series of simulations, you need mock data. The data are not useful for that. You need the theoretical galaxies. So you have a series of input galaxies, you fit them, and you see whether the derived mass stay on the one-to-one relation. As we publish here, it's easier to derive masses at redshift 2 than it is at redshift 0.5 because of the iceberg effect. At redshift 2, look at how nice the relation is. Galaxies have, the stars in galaxies have approximately the same age, so they don't overshine each other. While at redshift 0.5, if you have a second burst of star formation, the stars that have formed at a much higher redshift will be completely outshined. So you have quite a sizable offset which depend on your dust. In this paper, there is a table in which you can correct for this offset. So we are aware of it. Some ignore it, and they keep finding small mass galaxies at every redshift. I would almost consider trashable all these papers, honestly. Others instead say, okay, I find 10 to the 9, but I'm not looking at the 10 to the 9 solar mass galaxy. It is a 10 to the 11 with a delta. You can correct for that. Right. Likewise, your decoding of data depends obviously on the stars you put in. Your simulation will depend on the stars you put in to illuminate your galaxies. Now, this is a very fashionable field of work, which I'm happy to say we started, but I'm going to show you a very recent plot from the Durham group that have sent it to me. So these are, in this series of papers, we studied the effect of changing the population model in semi-analytic simulations. So this right-hand plot was the results of the model, which are the small dots, equipped with a certain population model. For redshift 2 galaxies, these are all redshift 2 with spectroscopic redshift, so there is no redshift uncertainty. And these are observed color and magnitude that show you how red is your galaxy. I don't know if you ever heard the problem of the red and dead galaxies. Some of us have heard that. Martin can complain that red can mean dust. I can complain that red can just mean asymptotic giant branch stars. Most people make a big fuss. That is the dark matter, the lambda CDM cannot make massive galaxies at high redshift. So we did this exercise. Indeed, if we take a semi-analytic model with the resident stellar population, the data that are the black point are completely off the simulation. The data are redder and more luminous than what the simulation would predict. Without changing anything about star formation rate and dark matter accretion, we swap with my model, which are intrinsically redder because they have these red giants. And now, the data are completely recovered by the simulation without making any difference in the dark matter or star formation rate recipe. Even they trace the few that are really red and bright in the right amount. So here we argue, before you conclude something on the formation of galaxy, make sure that you have proper stars into your simulation. And Violeta, Gonzalez, Perez, Carlton, Bow, and these people at Durham, in 2015, have shown the exact same effect. Here, this is shown, this is a class of objects that are called heroes, which is extremely red object at various redshift. And these are the prediction of semi-analytic model with a series of models they have inside. The red is Conroy, the yellow is, I don't read it. I have no idea, but it's something similar. They all line up, you see. This is all the difference in AGB or not. And the blue are my models, which, of course, as stated in the paper, it seems they are the only one that can reproduce this object unless you change the star formation. That's interesting for you to read. If you change the star formation in the model, made all the model passive with a lot of AGM feedback, of course, you get to the same results. But then you might not have that in nature. And also here, you are not okay because they are too bright. But just to tell you, this is really where you make the physics. Bruno request. With Bruno, we did the other thing, which is now interesting because it has also a lot of implication. In this plot, we check the quality of the theoretical spectral energy distribution in order to make the color. Now, the second question is, do we get enough high-mass galaxies that make up the K-band luminosity function over all the redshift range? K-band means near infrared. Why people did take data in the near infrared? Because the near infrared is where you trace the masses of galaxies. Here we work with 3 different galaxy formation models. The Millennium from De Lucia et al., Morgana from Pierluigi Monaco, and these people in Trieste, and Nicola Menci from Rome, and we will see the different things here is in the AGN feedback. But before doing that, we have calculated each model with either my models or the model by Brusol and Charlot 2003, which do not have much AGB, and then you see immediately the difference. So the data at redshift 3, 2.5, 2, even 1.5 and 1, let's say, at least the Millennium data, I actually nicely reproduced the high mass end by the combination of that AGM feedback plus my model. The other model are completely off, first, in all these redshift. And then second, towards the low redshift, instead, what makes a difference is also the AGM feedback included in the model. So it is, indeed. So the universe, it's easier, believe me, at redshift 2. Than it is towards redshift 0. And I know I'm giving another striking statement, but you see that. What happened here, this allowed me to include the second bit of AGM feedback. You should look at the papers by Croton et al. 2006. They have described all these things very nicely. You need 2 types of feedback. The quasar mode which is called quasar model, which act at redshift 2, which is quite strong, and is specific at that time. When you're building up the supermassive black hole, I'm going to show a result from Tiziana later, which have explained that type of thing. But then, because your universe is hierarchical, you need to have another feedback that prevent your massive galaxies from getting contaminated by too many successive mergers. And so people have invented what is called radio mode, which is of a less intensity and works on a very long time scale. Now, the difference you see between this galaxy formation model here is in the assumption of how you treat the radio mode, which I believe is quite complicated. And we need to study that. But you see also the interplay. If you start with the wrong stars, you can play with the AGN as much as you want, but you're not going to get to a sensible result. This is what I wanted to say. And this is again a plot. Now, you may wonder why I show so many plots by González Pérez. So Violeta is our new ICG Dennis Sharma Fellow. So every year we post a fellowship for 3 years. Thomas is laughing. The ICG has the money for doing that, luckily. And we post it usually in every field across astrophysics and cosmology, and we get to the person that qualifies better. So Violeta is from the Durham School, so she has done simulation with the GAL form code, and they have used at length my models and others. So we want to make now a lot of study based on galaxy formation models and try to understand how galaxies work out. Here again, you have a run of the whole global K-band luminosity function at two different ratios. I mean, these are things that we showed before, but their simulations are the newest. And again, you see that you need write the data. These are Conroy model modified a bit ad hoc, but they still don't make that thing. Good. So let me now guide you through what I think in 2016 are the most important facts in galaxy formation and evolution. I will be a bit arrogant in that I will neglect things in clusters, groups. No, I mean, it's not, first of all, I have to take out something. And also I think there are global lessons to take on which are quite independent of environment, as I will show. So the first things that was published now more than a decade ago by Piero Madao and Simon Lilly, but I'm showing a recent version of this plot, is the cosmic star formation rate. So the formation of stars in galaxies is not a flat function, although it depends on the bands you're looking at, I want to say, because in case of dusty galaxy may be different, but let's say globally. But it shows a peak at redshift 2.5. This is also the peak of the quasar luminosity function, and already put forward that the two things are related. This means here, of course, you are growing your galaxies, then you reach a peak. That's the peak that we discussed the other day. And then the universe is actually making far less stars at the present epoch, actually redshift below 2. First of all, most gas has been consumed, so the rate has gone down. Actually, in this consideration, there is no dark energy taken into account, which is something interesting to me. Maybe people are aware of it, because dark energy is a repulsive thing that also hamper mergers and hamper other things. And I wonder what the effect is. Now, first things, can the simulation recover that? Again, Violeta borrowed me one plot. I think this is from the Eagle. Eagle is shy and collaborator. This is a cosmic star formation rate in the simulation. Galform is the Durham Eagle, and L Gals at this moment I don't remember, so we need to look it up. However, you see that the peak at redshift 3 is reasonably well matched. It is flatter than the observation, and Eagle peaks at smaller redshift than the galaxies. This, of course, has to do with the ingredients. So I wanted to say, we are getting there. I think understanding the differences is the interesting part here. This is another pillar of our knowledge of galaxy formation and evolution, which is the existence of the black hole mass, or in this case, velocity dispersion relation. This was actually defined by Ferrarese and Magorian in the same year. And this is just a more recent version by Gultekin et al. What you see here, this is the black hole mass, and this is the velocity dispersion of the galaxy. A 10 to the 12 solar mass galaxy has a supermassive black hole in excess of 10 to the 9 solar masses. And look at how much they line up. Now, low mass galaxies do not have that. That's another problem in galaxy formation. You cannot give everything on the shoulder of the black hole, because there are galaxies strikingly without any central black hole. And they do evolve and feedback stars. However, the most massive galaxies line up in a nice relation that needs to be explained. Now, I'm very pleased to cite your paper, Tiziana. Maybe you're going to tell us how you did, because it is important. And in the simulation, I'm not aware of many works that have actually put the seed black hole and grow them together with galaxies. I don't know if this explanation holds at every redshift. There the problem is observational. I'm not an expert of that, but I know that measuring black hole masses at high redshift is just hell. It is reasonably complicated at low redshift, but at high redshift is problematic. Now, the ALMA telescope is going to do that, because it is sub-millimeter wavelengths. So we're going to see, because of course, this is the local relationship at redshift 0. The question is, how are these black holes built up? And do their growth follow galaxies, as also explained in this paper, or are they decoupled? So this is something to keep in mind. The other one comes from our own work and became famous as the anti-hierarchical baryon formation. So this deserves some wording. In this simulation, and this is still true in 2016, but it was particularly true a decade ago, the most massive galaxies were those looking the youngest. And the reason was that because of the many mergers, they could accumulate, even if they started to form at the highest density fluctuation at higher redshift or in clusters, they would accumulate the larger fraction of younger star. So what we did in this series of work, which that then state the point on this business, was to calculate the accurate star formation history of a sample of, in this case, of low redshift galaxies, using the chemistry instead of the colors. For what I explained the other day, magnesium and iron are ejected by different types of supernovae. So, if a population is rich in magnesium, it means the star formation was short and intense and dominated by massive stars exploding as supernovae type 2. If instead the population isn't rich in iron, as in our solar neighborhood, it means the star formation has been going on at a steady pace for billion years, and the low mass stars had the time to enrich the medium of iron. So the ratio, this is a very important cosmic clock, the ratio of magnesium to iron is telling you, without degeneracies, how long was the epoch of formation of the stars in your galaxy. And so we come out with this plot. We became very popular. This is redshift. This is look-back time. Each of these Gaussian, with which we approximate the star formation history, refer to different solar masses of galaxies. So 10 to the 12, 10 to the 11.6, 10 to the 11, up to what we call low mass galaxy. You see that the highest the mass of the galaxy, the highest redshift of formation, and moreover, and this is the dramatic result, the shortest. This, of course, you see, is anti-hierarchical. It's just the opposite, okay? Cowie et al. 96 called this downsizing, because it was looking, although, of course, not in such a quantitative way, at the same results. This we found in 2005, what we argue in 2010 using Sloan is that what is the driving parameter is the mass of the galaxy and not where the galaxy resides, because Sloan covers a lot of environment. And if a galaxy is massive, it doesn't matter where it is. And this is, again, this is a problem for galaxy formation. I come back to that. So, here you see what I mean, because this is one of the became very important scaling relation for massive galaxy. This is the element ratio between alpha type 2 supernova elements and iron. And this is the observed relation model for galaxies in the Sloan as a function of their mass at redshift 0. And then you see that the most massive galaxies are those having the highest ratio of alpha elements. There is a nice line with a small dispersion. The blue line here indicates low mass galaxies, and then go back to that later, in different environments. Now, what do both galaxies tell us? Because they give us a redshift span higher. The same relation is obeyed, and we are living with the most massive galaxies here. It means that, at least from redshift 0.5 to 0, galaxies, those, had identical stellar population, and there is no merger that can occur, because it would destroy this relation. Now, with the new instrumentation, people find the same thing at even higher redshift 1.4, using incredible data from the VLT. They find again the galaxies are enhanced strongly. And the other important thing is this does not depend on environment, and this was also shown using Cosmos by Peng et al. So this is yet to be explained. So if you want to have a good thing, not only the result at redshift 0, but the redshift evolution of this result, which it doesn't evolve. So in a nutshell, the chemical evolution and formation epoch of massive galaxies is currently not explained by simulation. And here I show the history of it. This is a plot by Thomas and Guinevere Kaufmann with the early millennium simulation, in which these are models. This is the ratio between alpha and iron as a function of galaxy luminosity, which means mass. These are the most massive galaxies, and these are the lowest mass galaxies, and you see that the enhancement is anti-correlated with the mass, which is exactly opposite to what the data show. And the disagreement is so striking, I always thought that there must be something very fundamental behind. And I'm convinced it's the cosmology and it's not the baryonic physics. So I give you this brief statement, but I think it is. Because this is, we think we are world expert of baryonic physics, and still you are not going to make that if your galaxy keep merging. So, but this I'm saying because you should be stimulated, especially those who do simulation, to try to constrain and recover this problem. I hope you're still with me. I don't do like Will if you have questions. Keep your question for the end. I'm showing you then, people have not seen passively this disagreement. In this paper, Gabriella De Lucia and collaborators have said, okay, alpha enhancement, that's the problem. We're going to put a strong AGN feedback in our simulation, because this is going to make your galaxies old. Okay, you quench star formation, you make your galaxy passive. That's obvious. So what happened in this simulation, which is very important, and especially we use the Sloan 4 to constrain, the conclusion was the following, that stars in the most massive galaxies could form early, thanks to the generous injection of AGN feedback, but it remains, and this is strongly lambda CDM dependent, that their assembly occur late. Okay, so you form your nascent stellar population 10 to the 6, 10 to the 8 solar masses at high redshift, so the stars are going to be old. For some reason, you keep preventing them merging further, and then you assemble your massive galaxy, and then you see from this plot that the assembly is at redshift 0.5 for 80% of the stars. This is a strong prediction, because redshift 0.5 is the redshift of the Sloan 3 baryonic acoustic oscillation experiment. So what we did was to try to verify in this paper that is the galaxy mass function from BOSS to check whether this is the case. So what you see in this plot is the mass function of galaxies at the massive end. You see that here only BOSS could give us these brutal statistics at the high mass end. If you check the Cosmos and all previous papers, you have huge error bars. Because if you get 10 to the 12 solar mass galaxy, you would be lucky. And so your statistics is terrible, and you would not constrain any model, okay? BOSS, and this is stated in this paper, we have the table, give us hundreds and hundreds of massive galaxies because it's target selected to trace the BAO. So you could really do this in a small redshift range, but still. So the BOSS data are the red. The fact that they need here is only target selection. We are interested in the massive end. And the blue are the Millennium simulation, binned in the same light cone as BOSS, and including also an Eddington bias here, which tells you essentially how wrong you're getting your masses in comparison with the observation. And you see that there is a lack of the most massive galaxies in the simulation, which was known before, but it was not put on a statistical basis with respect to the data which now contain the largest number of massive galaxies. So, I was chatting with some of you the other day. Most of you are familiar with the dwarf problem of the satellite. But the massive end is far more interesting, in a way. Because this is really, there is a lot of complicated physics, but as the state of the art, we lack the most massive galaxies, and we lack them with the right stellar population. This was just an example of how the model grows. Because it is a hierarchical, we jump from redshift 0.5 to 0. At redshift 0, the model is above the observations. This is published by Lee and White. And the reason why it's above is because it keeps growing galaxies. So the trend of the model is very clear. And so the other thing that you should keep away, so the number of galaxies is incorrect. What about scaling relation? And I think this is where the simulation should actually get to improve. These are the model color of galaxies, a function of mass. And these are the data as a function of mass. And you see that the data display what is known from the 70s, the color magnitude relation, telling us that the most massive galaxies are the most matter-rich, or the reddest, but not because of dust. The simulations are flat. You see that the colors don't change as a function of mass. The reason is it's all. The metallicity is mostly driven. I mean, there are simulations that are making a lot of effort in that. So this is what the semi-analytic models say. The hydro simulation, of course, take metallicity in a more sophisticated way. But still, you don't have this relation. Exactly, you expect a dilution of metallicity. And for example, minor mergers, in this sense, are a killer because they bring in dwarf galaxies, which have another metallicity. And this is just to say that this was also discussed by De Lucia and Borgani, Sackstein and Pipino. They all find consistently that the metallicity in the simulation is too low, both in stars and in gas. So it's all the evolution, you see, because metallicity evolved because you evolve your galaxy. I'm approaching the end in a figurative sense. And now I want to show you, because you are all involved in Sloan, the next of Sloan is Sloan 4. Sloan 4 has several projects, including eBOSS. For extending, for example, I would use eBOSS to do the mass function at higher redshift. But there is a project which is called MANGA, in which, so far I show you global property of galaxy. Now let's go through a galaxy and see what happens. So MANGA, PI is Kevin Bundy, is an IFU, what is that? Integral field units, thank you, Magda, in which you have a lot of fiber and you view at the galaxy overall. You can do that at redshift 0. There are also instruments for doing the entire redshift, but this is tough because essentially you are not seeing at the whole integrated light, but are viewing at the whole galaxy. So we did the first spectral fitting in this paper. Here you see maps, and now we have maps. This is, you have no idea, this is revolutionary. When I did the PhD, these things were inconceivable, and I'm not that old. So here you have your luminosity weighted stellar age map around this galaxy. And you see that the age doesn't change. Okay? The bulge is a little bit older, which it's okay. Now, if you plot this comes from Daniel Goddard, who is one of our PhD students, you find gradients. Radial gradients means how much your stellar population varies as a function of radius. This is age gradient, which is quite mild, 0.058. The average is actually 0 over all Sloan 4 galaxies. Metallicity gradient, very sharp. I mentioned at the beginning of the hour monolithic collapse. This gives you exactly this number. Because, of course, you start with metal poor, cook the metallicity, go into the center, and you build up your metallicity gradient. As Simon White published, merger destroy gradients. So they flatten it. That's obvious, right? Because you are putting in population coming from different sources, and the average becomes much less pronounced. So these are results yet to be published, but it's now. This is the last of the outlook. Because you are all cosmologists, so 90% of you, I show you how we use cosmology to do galaxy evolution. The other thing is the dark energy survey. Boo spoke about lensing, there are nice things, blah, blah. For our point of view, which is published here, the interest is DES is large. Meaning, because the most massive galaxies are rare in the universe, you need a super large survey to catch them. And in this plot we show, these are other surveys, very important actually, that only the dark energy survey can actually catch massive 10 to the 12 solar mass galaxy at very high redshift. Okay? If they are obscured completely by dust, that's another thing, and we discuss it in the paper. This is important for the simulation. Here we put the prediction on how many of these galaxies we could catch as a function of the mass. These are the most massive galaxies, and this is their number normalized to the area of DES. Now, the green is the Millennium simulation, which predict 0 galaxies here. Okay? These lines, instead, are extrapolation with passive evolution of present-day mass function. Unless massive galaxies break in small pieces, you should find a sizable number, where sizable can be calculated precisely of massive galaxies. And I'm very pleased to show you the first detection. These are plots made by another PhD student who just sent it to me last week. So these are plots that show there are redshift larger than 4 in this case, and larger than 6 candidates in the dark energy survey. This is the mass of galaxy. Of course, maximize a redshift before 1, because that's wanting to do cosmology, mostly redshift below 1. But you have a tail. The numbers to us seems good exactly to reproduce the ratio of the numbers that we would expect at this very high redshift. And so this we are going to publish. Now this is going to be quite striking, because in fact there are more galaxies than at this high mass, these are all 10 to the 12, than predicted by any simulation. I'm finishing. I took the time to, because... So, just quickly, my solution would be change star formation efficiency. This is parameterized with the Koenig-Schmidt law for all galaxies, and I don't think that's the right thing to do, but also change cosmology. I don't go about the cosmic chronometers, and I finish here. Thank you very much.
Well, we have time for a few questions.
We should not make it too quick, because yesterday we received class. You may not know. It's important to get there. We should have less time.
Hi, these are very interesting results. So what kind of changes in cosmology do you expect to see from these results?
The cosmology should allow to form structure earlier. Okay? This can be accommodated with some dark energy. I know that because in Portsmouth they're doing that. I'm not an expert of this, but clustering structure at an earlier epoch. But the other problem is to keep them pretty much untouched all over the cosmic time, at least at the massive end. So you need to form the galaxy in an old-fashioned monolithic collapse, 10 to the 12 solar masses, a Rashi 4, and then let them there. Now, this is difficult. When I see the simulation, for example, Chaki Kobayashi came to give a talk. In order to make the bulge of the Milky Way, she has to artificially drop every merger before Rashi 2, which is a long time. So that is the two directions. So you need to make a mild evolution to start it earlier. Which cosmology gives you that? I don't know yet. You should think about it.
Can you give us a quick summary of your view on the cosmic chronometers and whether they're systematics that...
Yes, happy to do that, because we will not have coffee, which is okay for our health. So, the cosmic chronometers, just quickly. I know, I promised that, especially to him. The cosmic chronometer means, and now you believe me, that we can get super precise ages of galaxies. The ages of galaxies don't depend on cosmology, so we use them to constrain cosmology. So in this work especially, Moresco et al. Have calculated the ages of the most massive galaxies in the universe. Of course, you want galaxies that don't evolve too fast, because otherwise you are measuring their fluctuation in star formation more than the age of the universe. So you measure that, assume they evolve parallel to the time evolution of the cosmos, and evaluate the Hubble parameter. So these are points, and these are a plethora of cosmological model with different value of W, and the standard lambda CDM is the solid line. The systematic that Eric was alluding to, which here reduced to the minimum, are the fact that if the ages of galaxies are calculated with this model, Brusal and Charlot, you get this trend, which at the highest redshift, it seems to go against lambda CDM, or it starts to separate away. Here, the ages are calculated with my models, and you get another answer. Okay? That's the problem, at the highest redshift. This is state-of-art work. I'm going to show you another plot. If you want my opinion, this is due to the different overshooting, core overshooting in massive stars, which I explained the first day. Okay? It's the fact that this model assumes that overshooting has a certain size, they burn more hydrogen, and the ages are different. In this case, I do not assume overshooting. I think I could spend a few slides to convince you that there isn't much overshooting, not as strong. However, keeping a Solomonic neutral approach, there are other situations coming from the high redshift. This is what Olivier Lefebvre is doing, cosmic chronometer redshift 5, and going down back to the redshift. This recipe seems to fit the spectra better. And then you will take, because here what you don't see is the chi-square of your ages, how well they are determined. So looking at those, you can break this degeneracy. So my opinion, because I think this is a super powerful technique because it exploits baryonic physics independently on the curve, I think we are in an epoch in which we can take opinion on the systematic and try to make the exercise. In fact, we tried, and Nature refused the paper. Sorry. Now it is submitted to the APJ. So this is the 2015 version using both data. You can believe me that these error bars are the best you can have, and they are comparable to other determination, the Lyman alpha or other stuff. And this is what this is work mostly done by Raul Jimenez in that collaboration has assessed the redshift of the cosmological transition. This paper is an astro-pH, so you can get it. Nature has refused it. And now it is submitted, but you can have a look at that and we can discuss it over the next few days.
Well, we must stop here. We thank the three sessions of the course. Very, very, very nice course.